0. This is 0. Right? Because on a unit circle, the x-coordinate here is 1, right? The x-coordinate is 1. So you're saying at what angle is cosine 1? That means your angle has to be 0 degrees. So this right here is saying cosine inverse of m, right? Look at m as being m over 1. Do y'all see m over 1 here at all? This would be m over 1. Do y'all see that? M over 1 like this. So cosine inverse would be, man, I really do think I'm going to, I think I'm probably lost 85 to 90% of you. Is that a right assessment by looking at your faces or not? No? I don't know how much more I should do of this. I'm trying to get us to see that this is x, right? Let me do it this way. Let me do it this way. Let's graph the original function. Arc cosine of sine of x, right? Okay, great. That's what I was hoping to see. Arc cosine x. So look at this. That is a weird graph. I thought we said that it was going to be x. I need to erase some of this. I thought we said that since our derivative came out to be -1, I thought that meant that this thing should have turned out to really be -x, right? I thought that's what we had said. Well, I think it's clear from the picture that that is not -x, right? -x, this is x, this is -x, right? Right? Okay, but it's the slope of the tangent line, right? This is the slope of the tangent line. Do you see a slope of a tangent line on that curve as being -1 somewhere? How about between here and here? Doesn't that look like the slope of that? If you pick any point on this curve, do you agree that the slope of the tangent line would be -1? Yes? Now, why is it that I'm only going to look between here and here? We have an arc cosine function, right? Which means that we have restrictions of where we can look. So the arc cosine function, you're actually only supposed to look between -1 and 1. And -1's right here. I mean, sorry, +1's here and -1's right here. So if we just look between here and here, do y'all agree that that basically is like the -x function? But it looks like it's been moved up a little bit, doesn't it? Okay, so would that change our answer? Like, let's say I move that up 3. Is the derivative still the same? Yes, it is, because a constant has no impact on it, right? We'll do more of that in Cal 2. You realize that when you're trying to go backwards from here to here, you always have this constant that you can move up and down. But all right, I think we should proceed because we can get buried in that problem if we think about it too much. All right, the nasty one. We can do a nasty one, yes. Okay. This one. Y is equal to arctangent of the square root, oh wait, the square root's on the outside. Square root of 1 minus x over 1 plus x. How are we doing on time? All right, good. Well, since you asked for it, right? Okay. So what's the derivative of this? This is composition.
Right. So
of arctangent of something, right?
So it's 1 over.
1 over
1 plus
1 plus
that something
that something squared. And that something is all of that, right? Squared, which is actually nice because when you square the square root, it goes away. So I get 1 minus x here over 1 plus x. We all on board with that? Now, we're not done. Because now we got to finish by taking derivative of what I circled here. Quotient, yes, but not yet. Because you've got the square root on the outside of the quotient. So you can now take the derivative of the square root of something. So the derivative of the square root of something is 1 over 2 square roots of the something, which is now times the inside of the root, which is going to be a quotient rule. So we have to do a quotient rule on that piece right there now, right? And I'll just do that on the side. I'm just going to do it right here. The derivative of this quotient, James, where's James? James, I want you to just focus all your attention, James, on this right here. And give me the derivative using the quotient rule. So just kind of piece by piece.
So it's negative 1.
Negative 1
times 1 plus x.
times 1 plus x minus
1
1
times
1 minus x
over
all over
1 plus x.
1 plus x squared. Good. Excellent. And now we just clean that up. All right, so I'll distribute negative 1 through, distribute negative 1 through, and let's see what we get. So negative 1 minus x minus 1 plus x all over 1 plus x squared. And I believe my x's cancel. And so all I get is negative 2 on top. And on the bottom I get 1 plus x quantity squared. So there it is. Yep, these 2's can cancel. So that's where I am, right? That is the derivative. That is the raw derivative. So it's nasty, but it's not too bad. Cleaning this up algebraically is nasty. So should we clean it or not?
No, let's just leave it like that.
You should leave it like this? Let me just tell you what you would do, all right? You would first get a common denominator between these two. Okay, so imagine that you put these two together. So you've made 1 over 1 here. You put those together, right? When you put those together, you're going to have a fraction down here. 1 over a fraction is the reciprocal. So like basically whatever you get here, you're going to flip it and you're going to have that here. Here what you do is you break this root into 2 fractions and then you flip it. So you'll have a fraction here with the root on top and bottom. And then over here you have a fraction. It's negative 1 over this thing. And then you put them all into one fraction and some of the things are the same and they'll start canceling out.
Can we do 1 minus x over 1 plus x to the 1/2 that?
Where, here? Yes.
Negative 1/2.
This right here would become 1 plus x to the half over 1 minus x to the half. Is that what you're saying?
Yes.
Yeah, so it would be this to the half over this to the half, and then that flips over. And then next to it over here, you have whatever you get when you get your common denominator. Let me just do it real quick. 2, this will be 2 over that, but then it flips. So it'll be 1 plus x over 2, I believe. I don't trust it now, to tell you the truth. And then this over here. So you can see if you do that, that this, and this, those are all the same. So you can start messing with powers and start canceling things out. All right, I'm not doing it. All right, so now you have a homework assignment for this section where they're just going to start throwing a bunch of things at you, where you're going to be using product rule, quotient rule, chain rule, but now you've got these 6 new trig functions to play with. The only way to get good is to just practice, all right? Without going through the whole problem, how do you think you would do something like this? How do you think you would do that? Find y prime. Okay, so this is that implicit differentiation. Here's where you cannot solve for y. You can't get y by itself because it's trapped in here and it's over there. So this is where you take derivative with respect to x on both sides. So what would the derivative of this be with respect to x? You go 1 over 1 plus whatever's in here squared times the derivative of what's in here, right? Which would be a product rule. Well, shoot, we've gone this far, may as well. What's the product rule here? So derivative of that, 1 times y squared, plus, this is the crucial part, derivative of y squared, 2y, drum roll, times dy dx. Because when we take derivative of y squared, the 2 comes down, times y, then derivative of y is dy dx. So you have y prime, that's dy dx, and then still times x. Y'all see, that's our product rule. We've done this for a while now. That's our product rule using implicit differentiation on that. And then we're done with the left side. So then we go to the right side. And derivative of 1 is 0, and then here we have another product rule. So it's going to be 1, derivative of that's 1 times y, plus derivative of y, which is y prime, and then times x. And now at this point, you would have to try and clean this up algebraically. And it might be messy because this has to get passed through. So on the homework, I do this problem, and you'll see me go through and pass it through and clean it up and stuff. I think I clean it up. All right, so really, look, there's no new type of differentiation. There's no new. The only thing that's new is these functions now. Like we have new functions that have new derivatives. So now you just have to be able to play the way you've been playing with everything else. And then we move to the next section, which is 6 more functions. But this will be the end. This is the end. This is the last 6 functions, and then we can proceed into the class to something different. Now, most of you have never seen hyperbolic functions. I would guess that nobody here has. I could be wrong, but usually hyperbolic functions are not introduced in pre-cal at all. So let's define a hyperbolic function. These are what? What are not? The hyperbolics, yeah, I'm just going to go through them very quickly. Yeah, on our schedule, there's no homework from this section. Usually in Cal 2, you will go through this section completely in Cal 2. I just want you to see them, okay? So we have these things called hyperbolic trig functions, and they are very weird, all right? They're very weird because, well, first of all, here's the way you write it. You write like sine x, but you put an h there, and that lets you know you're talking about the hyperbolic sine function. And look at, this is the definition of it. This is not the derivative of it. This is the actual definition of hyperbolic sine of x. So just by looking at that definition, if I ask you right now, what is hyperbolic sine of 0, that means all you're going to do is replace 0 in here for x. So that'd be e to the 0 minus e to the negative 0 over 2. And what's e to the 0? That's 1 minus e to the 0 is 1. 1 minus 1 is 0 over 2, so you get 0. Sine hyperbolic of 0 is 0. And you could just do this for any number. Plug numbers in here. Would y'all like to see the graph of the hyperbolic sine function? Sine hyperbolic x. There it is. That's what sine hyperbolic x looks like. And then you have cosine hyperbolic, which looks like this. Now this one is actually a very, very interesting function. And I'll explain why it's interesting. If you were to take, let's say you take 2 poles, the same height, and you take a rope and you suspend the rope between the 2 poles. Okay, so it's just hanging there between two poles. I mean, you see this every day, right? You go drive down the road and you see the utility poles, you see the electrical wires hanging from pole to pole, right? Okay, the shape of that wire, this shape right here, is actually not a parabola. Like, it's impossible to come up with a parabola that would draw that curve. You might get it to look pretty darn close, but you can't do it, all right? So any hanging wire is not parabolic. It is actually cosine hyperbolic. So when you graph the cosine hyperbolic, this right here is the shape of a wire hanging from two poles. All right? It's not easy to prove that, but it can be proven that that's what it has to be, this function, cosine hyperbolic of x. So what's nice about that is, you know, one of the things you could do in like a physics class is you would say, let's say you have an anchor point here and an anchor point here holding this huge wire up, and you want to know like how much force is being applied to that anchor point. Well, the first thing you would need to know is the slope of the tangent line right there, because the slope of the tangent line would tell you the direction in which the force is pulling. So to find the slope of the tangent line there, you would need to take the derivative of this hyperbolic cosine function. So all I want you to see here is that there are 6 new functions. You're not going to be tested over this. That's tangent hyperbolic, and then secant hyperbolic, looks like that. So there's 6 of them, and for each of the 6, here they are, they all have derivatives. So just be aware that on your formula sheet, you have those. I'm not going to test you on these, all right? But be aware that each of the 6 hyperbolic trig functions have derivatives. And look, they're actually very similar to what we've seen, right? The derivative of sine hyperbolic x is cosine hyperbolic x. Yay, that's exactly what it is when it's just sine. But this one's different. Do y'all see that? Derivative of cosine hyperbolic x is not negative sine hyperbolic. It's just sine. So some things are different. The derivative of tangent hyperbolic x is secant squared hyperbolic x. That matches what we've seen already. So you have 6 functions. 6 functions, 6 new functions in 6 new derivatives. And I've got bad news. Each of those 6 functions have inverse functions. So each of the hyperbolics have inverses. And then each of those inverses have derivatives. All right? So if you were to, this is it. This is the end of functions for us in here, okay? Like if you were to sum it all up, you've got your trig functions, right? You've got sine, cosine, right? How many of these do we have?
6.
We have 6 of these, right? Then we have all their inverses, right? Sine inverse, cosine inverse, right? And we've got 6 of those, right? Then we have our hyperbolic ones. Hyperbolic sine, 6 of those. And then you have the inverse hyperbolics, right? And you have 6 of those. So that's like the final tally, all right? This is all of them. And for each of these 36 functions, they all have derivatives. So on your formula sheet, you will find every single one of these and every single one of their derivatives. So down the road, if you're ever in a physics class and you have to take the derivative of hyperbolic sine of something, it's there, all right? And they all follow the chain rule the same way everything else has. All right, we have 10 minutes. We have 10 minutes. And I don't want to get too deep into this because I think you need a weekend just as bad as I do right now. But I at least want to just glimpse into it, all right? Because I don't want to sell you short. 10 minutes is 10 minutes, right? I want to go back to a limit that I want to take a look at a limit that we've done in the past that really sucked when we took the limit. It didn't really suck, but it wasn't fun. let's say limit theta goes to 0, tangent 4 theta over sine of 3 theta. Let's see if you can pull that out of your brains. Do you remember at all how we did this? How?
You break it into sine over cosine.
Yeah, you started splitting it up into like sine over cosine, and then you start like, oh, I need this over here, so I introduce something, then slide it over. Does that ring a bell at all? It was really a disaster, right? I'm going to work it real quick just so you can see, remember what I'm talking about. So the way I would have done this problem in the past is I would have done this. I would have introduced a 3 theta on top and a 3 theta on bottom. And the reason why is because I could take this 3 theta, slide it right here, make that 3 theta. That's really gone now. It's a 1. And now what does this go to?
1.
That goes to 1. But now we have a problem because when I go to 0 here, this goes to 0. 0 over 1, 0. This goes to 1. That's 1. This goes to 1, but this one now has division by 0. So this is when I would take that theta and I would slide it over here, and I would need a 4 theta, so then I would introduce a 4 on top and 4 on bottom. And slide the 4 over like that, and then leave that 4 there.
But then you can take the 4.
That theta's gone. So this one now would go to 1, this one goes to 1, this one goes to 1, and then what's left over here? I took this one over there. So you have the 4 on top and then the 3 on the bottom. You get 4/3. Okay, so you remember how much work that was? Yes.
Remind me why you wanted to take the additional 4 and put it on top of the cosine 4 theta?
Because that wouldn't, this is not a problem. As theta goes to 0, cosine of 0 is 1.
Oh, right.
So that's not a problem. So even if you put the 4 up here, you get 4 over 1, so that would just be 4. All I want you to do, I'm not like reteaching this, I'm just kind of reminding you how this was bad, right? Okay, so I would like for us to do something else here. Just for the sake of doing it. Don't ask me why. Just do it. I would like for you to take this right now, and I'd like for you to take the derivative on the top and on the bottom separately. So what is derivative of the top? Secant squared of 4 theta, one more thing, very important, times 4. That's the derivative of the top, right? What's the derivative of the bottom? Cosine of 3 theta times 3, right? Now, I told you to do that. I didn't explain why. But now I'd like for you to do the limit again. All right, so let theta go to 0. This goes to 0. What's cosine of 0? 1, right? So the bottom is 1 times 3. So the bottom is 3. And now on the top, do the secant part first. So when you plug in 0 here, you get secant of 0. Secant of 0 is the same as 1 over cosine of 0, because that's the reciprocal. Oh, 0, not theta. Right? That's secant is the reciprocal of cosine. So that's 1. So you just get 1 here, don't you? So secant of 0, when you let theta go to 0, this is secant of 0, that's 1. 1 squared is 1, and 1 times 4 is 4, and you get 4/3. And that answer is the same as that answer. Right? Okay. Is that not nice or what? Super nice. Do you remember this problem? Limit x goes to infinity. Something like this. 3x squared minus, or let's say plus 1 over, let's go x to the 4th. We'll make it 5x cubed minus x. Do you remember how we would do something like this when we had infinity over infinity? We would have to come out here with something out front. Remember that? And push it through. Do you remember that? Yes? Okay. I want you to take the derivative of the top and bottom right now. Derivative of top and bottom separately. So what would you get on top? 3x squared. And then on the bottom, what would you get? 15x squared minus 1. Now try and do the limit again. Don't we still get infinity over infinity? Yes? Do what I told you to do again. Take derivative of top and bottom again. So what's the derivative of the top? 6x over the bottom? 30x, right? That's it? Look, the x's cancel this time. And what are you left with? 6 over 30, which is really 3/15. That is the limit. If you did what we did in the past, you would get this answer. What I'm telling you is that there's a new way to do limits. And you just take derivative of top and bottom and then do that answer. We can do this one too. Yeah, I still have minutes. Remember the one I asked you to memorize in the very beginning of class? I said memorize this, but don't ask me why. That this would be what? This limit is what? 1, right? I said memorize it, memorize it. But now I'd like for you to just take the derivative of the top and bottom separately. What's derivative of the top? Cosine x. What's derivative of the bottom? 1. Okay, now let x go to 0. Cosine of 0 is 1 over 1. The answer is 1. Okay? This is what's called L'Hopital's rule. And it's a new way of taking limits. And it's pretty nice, right? So every time we do this, people get all pissed off at me. And they're like, why didn't you just show this in the beginning? Right? Like, why make it so difficult? Why make it so hard? Why not just give you L'Hopital's rule to start? Which I think is a good question. But I think you can answer your own question if you just think about it for a second. What did we start this class with? Limits, right?
We learned limits before derivatives.
That's right. We learned limits before we learned derivatives. We used the limit, then we used the limit to define the derivative. And then we started to do a bunch of things like rules and all these different things. What's happening here in 3.7 is we're saying, hey, guess what? You can actually use derivatives to come back and do limits. We could not have done this in the beginning, because if I would have given you this in the beginning and said, oh yeah, to show that that's 1, just take the derivative of the top and bottom, you would have no idea what I'm talking about, right? Yes?
I think it's a metaphor that you could use to answer these future questions, which is ask them, what do you know, what do you have to learn first before you run? And that answer is crawl. You have to crawl to walk and walk to run. So when you combine crawling and walking, you get running.
Or the horse, don't put the, what is it? Don't put the horse in, you've heard that one? Don't put the buggy in front of the horse. Have you heard that? I mean, we can't.
Yeah, you can't move the buggy.
Yeah. Well, you don't want to put the buggy in front of the horse, right? So we have to get the order of things correct. Your homework for this weekend and what would potentially be on a quiz would be anything from 3.3 still, natural log, this stuff, okay? Because maybe this quiz didn't go well. I don't know. I have to grade them, but that's fair game for the quiz next week. And then 3.5, which is your inverse trigs and the derivatives. So make sure you do that homework, and we'll come back next week and we will start L'Hopital's rule.
You pronounce that hospitals?
It looks like La Hospital, right?
Yeah.
Like La Hospitals, but it's actually L'Hopital. Yeah, L'Hopital. All right, everyone, have a good weekend.